August 15, 1977. The hushed control room thrummed with the faint hum of reel-to-reel printers. Volunteer astronomer Jerry R. Amon leaned forward, pulse quickening as each line of data scrolled beneath his pen. Night after night, the lines had whispered only cosmic background noise, steady, familiar, unremarkable. Then, amid the ordinary hum, 6 characters leapt from the page. 6, EQUJ, 5. Amon paused. Silence. He picked up a red pen, circled the sequence, and scrawled one word in the margin. Wow! In that moment, the radio sky spoke in a way no one had ever heard before. More than a decade earlier, engineers at Ohio State had repurposed a decommissioned radar array into the Big Ear, an imposing tilt-over radio telescope fixed in place. It could not swivel or track. Instead, Earth's rotation carried the heavens through its twin horns. Each beam was barely 4 arc-minutes wide, so narrow that a fixed source would drift through one horn, then exactly 3 minutes later through the second. Scientists tuned Big Ear to 1,420 MHz, the natural emission line of neutral hydrogen. They believed any advanced civilization broadcasting a greeting might choose this universal frequency, the hallmark of the cosmos's most abundant element. That late summer evening, Amon's printout revealed a sudden spike in one beam. Over 72 seconds, the exact time a steady extraterrestrial beacon would remain in view, the signal's strength rose, crested, and faded, tracing a graceful bell curve. It occupied a single frequency channel among dozens of adjacent bins, dominating the background noise. And when the telescope's horns completed their drift, the second beam remained silent. A single event rising 30 times above the ambient hiss of space, marked in the printout by the character U, was virtually unheard of in natural astrophysical processes. What had pierced the cosmic static? Big Ear recorded signal intensity as alphanumeric characters. A blank space signified no detection. Digits 1 through 9 marked incremental rises above baseline. Letters A through Z corresponded to larger jumps of 10 sigma increments. Sigma, a statistical measure of signal strength, reflects how many times above background noise a signal registers. Thus, 6 represented 6 times the noise, E equaled 14, Q and U corresponded to 26 and 30, then J before tapering back to 5. The sequence sketched a symmetric peak, the exact shape expected when a stable source drifts through a fixed antenna pattern. It read like a deliberate call from beyond. With only one detection, the team faced an agonizing question. Which horn had recorded the burst? Ambiguity over the feed horn translated into 2 possible right ascensions, roughly 19 hours 22 minutes and 19 hours 25 minutes in equatorial coordinates, while declination held firm around 27 degrees and 3 minutes. The likely patch of sky lay deep in Sagittarius, near globular cluster M55, and east of the Milky Way's bright central bulge. Yet without a second confirming hit, the signal's true origin remained a pinpoint too small to target precisely, a dot in the southern sky that vanished as swiftly as it appeared. In the months and years that followed, Amon's heartbeat quickened with each new observation. Night after night, the Big Ear team returned to the Wow Patch, scanning for the telltale narrowband pulse. Silence, then more silence. Other observatories joined the hunt. The Meta Array at Oak Ridge, the Very Large Array in New Mexico, Tasmania's Mount Pleasant dish, dozens of sessions, hundreds of hours, 0 repeats. If an intelligent civilization had transmitted a beacon, why broadcast only once? If natural, why mimic the telescope's drift signature so perfectly? Decades later, in 2016, a new explanation emerged. Astronomer Antonio Paris proposed that comets 2266P Christensen and 335P Gibbs had drifted through the WOW coordinates, their hydrogen clouds emitting the 1420 MHz line. Could cometary outgassing mimic an interstellar beacon? Yet the theory unraveled under scrutiny. At the moment of detection, the comets lay just outside Big Ear's narrow beams. No similar emission ever appeared from those comets before or since, and a diffuse cloud of hydrogen would never concentrate into a single frequency bin or follow the telescope's beam response so cleanly. The hypothesis collapsed, and the mystery deepened. In recent years, some researchers revisited archival narrowband data for clues. In 2023, scans from modern arrays teased faint sporadic bursts near the WOW locale, perhaps from magnetars or neutron star flares. Magnetars, highly magnetized neutron stars, can unleash intense radio and X-ray flashes. Could one such flare have aligned perfectly with Big Ear's view? The new signals, however, lack the WOW signature's clarity and timing. The tantalizing prospect of an astrophysical origin lingers, but until a clear repeat with the same bell curve profile appears, the theory remains speculative. The WOW signal resides at the crossroads of rigorous astronomy and hopeful imagination. For SETI advocates, it is the closest brush with first contact, a signal matching every textbook expectation. Skeptics counter that a one-off pulse, uncorroborated by other instruments, falls short of proof. Could a rare reflection of orbital debris, a passing satellite's transmitter, or a glitch in the telescope's electronics masquerade as an interstellar ping? Eamon himself, years later, admitted these possibilities even as he held fast to the signal's remarkable alignment with expectations. In science, replication is everything. Without it, the WOW signal remains a compelling question mark. Over 4 decades, the WOW signal has inspired a rich tapestry of stories. It features in History Channel documentaries, podcasts exploring unsolved mysteries, and popular science books chronicling SETI's near misses. Every August, amateur astronomers point backyard dishes toward that patch of Sagittarius, hearts racing in hopes of a reprise. Online forums brim with fresh theories, from exotic plasma physics to alien beacons, ensuring each anniversary rekindles public intrigue. In classrooms, the WOW case study teaches students about signal processing, statistical confidence, and the challenges of one-off events. Today's telescopes dwarf Big Ear in sensitivity and scope. FAST in China, ASKAP in Australia, and the global breakthrough LISTEN network scour the skies with unprecedented power. Yet none have captured a WOW-like burst. This silence underscores a profound truth. The universe may whisper in frequencies we scarcely detect. A fleeting, perfectly shaped signal from 46 years ago reminds us that even our most advanced tools can miss the moment that matters most. The WOW signal teaches humility about our ingenuity and our limitations in probing the cosmic expanse. Imagine yourself at the controls of a silent receiver, antenna poised under starlight. The cosmos beyond is vast and inscrutable. What if a single pulse holds the key to answering humanity's oldest question? Are we alone? Each scan, each data point could be our next wow, a message waiting for someone patient enough to hear it. Will we recognize it when it comes? 46 years ago, Jerry Amon circled 6EQUJ5 in red ink, capturing a moment that transcends proof. Big Ear is long gone, repurposed into new projects. Yet the wow signal endures, an invitation and a challenge. The universe speaks in frequencies we have yet to master. In that singular, enigmatic pulse, we glimpse our longing for neighbors among the stars and our resolve to continue listening. Lean in. The next call may already be waiting. Hit subscribe, ring the bell, and leave a comment telling us which mystery you want unraveled next. Your curiosity powers our exploration. Join us on this voyage through time.